Okay, good. So as you said, we are among friends. So I dare to say a couple of very provocative things. So let's see where we get with this. These are just some thoughts that have been kind of bugging me for the last, well, basically because of all these nice discussions that we have had. So, well, this is a nice example of causality, I think. This is a very brief story about Borneo in the 1950s, when the Dayak people there living there were massively dying from malaria. And then the head of the people asked for advice with the World Health Organization, and they said, apply this DDT. And so that's what they did. And then as a consequence, which is an interesting thing, as a consequence, the roofs start to collapse in the villages that were actually having these problems. So the consequence of applying DDT was that the roofs were collapsing. I think that's a cool thing to see. Another consequence was that the cats were dying, and another consequence was that the plague started to come up. And well, to cut this long story short, explanation was, of course, the chain of events, and the chain of events was that the DDT also killed the wasps that fed on the caterpillar, and the caterpillars were then not eaten, and because of that, the caterpillars they were eating always the thatch that's on the roofs, and so because of that, the roofs started to collapse. So that's an example of where we see how an intervention comes with all kinds of weird consequences. And so we talk about cause and effect. This, I think, is an example where you see that there is a kind of across, you know, there's a kind of wave of causality moving around and getting in all kind of, I would say, peripheral possible consequences. I won't go to the other stories here. Well, the last science sentence does make sense. If you don't understand the interrelation of things, solutions often cause more problems. Now, the thing is that, I need to remove this thing a bit. Okay. The thing is that, that we see a lot of nonlinear causality in our interventions. And here is an example. So one of the things that we found in our own research is that if you close the most segregated school in a large city area, then it will actually result in more segregation in the school system, which is a totally weird cause and effect relation. Other research from ourselves, if you take out the kingpins of a cannabis production, it actually makes the production more efficient. Again, a very weird cause and effect. Another thing from our own research, if you have better HIV medication, it might lead to more HIV in particular populations, and this was particularly in the homosexual population. And by now we all understand the whole cascade, if you like, of how this causes and effects play together, but they're completely counterintuitive. Closing segregated schools, more segregation. Better medication, HIV, more HIV in a population. It's something which is counterintuitive in all many ways. And this is really, I think, for us at least in our research, the question where we, want to think that we want to better have understanding of how do you quantify, how do you measure, how do you explore this cause and effect, and what are the limits of it, which is the question that Federica asked us to think about. So what we need to do, if we want to understand this cause and effect, we really need to make the problem bigger, if you like. If we want to understand what's happening, for instance, on the organ level in an individual, we have to go down all the way to the tissue, to the cell, to the molecular level, and all the way up to the environment. Everything is connected to everything. And but yeah, you have to figure out how far that connection goes and how far that connection is relevant, which is, I think, the fundamental question to ask in cause and effect. So I kind of thought, as we are among friends, I come up with the definition of causality. This is my preferred definition. So causality is something that indicates the state of a system after a predefined period of time, and the period of time should be less than zero, or should be not zero, after a predefined period of time since an event, with or without intervention. So something that indicates the state of a system that I'm studying after some time, since an event has happened, with or without an intervention. Both aspects are important here. And as a consequence, causality also has a value. It's not that just this is causing that, but it's also causing it to some kind of extent. And there is time there. So the example that you saw in the thatched roofs, it's not directly. It takes some time before you see that effect, and then then you can start to try to unravel that cause and effect. So causality has a value. It might has you might equate that to a strength. You might consider it even like a field. I like to think of causality as a probability force field. And if that's true, it actually opens a whole toolbox of trying to quantify causality, which we're not going to talk about today, I guess. But so this is for me an important thing. So I define the causality like that, and as a consequence, I can think of it like a probability field. And that means that I can do all kinds of nice things. I can think about the work done in. I can think about the work done in the causal system, because I actually just integrate across the field. And I can interpret that as the equivalent to basically reducing the uncertainty about the state of the system that I defined in the first bullet. And reducing uncertainty is, of course, gaining information, and that for us is the link to information theory. So if we move along the force field of that or probability field, if you like, the causal probability field, then you can play these kind of nice games and understand. The more you get the information about a certain causal relation, you build up, you reduce this uncertainty, and you can quantify that in the amount of information being gained. There is kind of funny thing, I think Kees might like that. So if you have a lot of those events according to those definitions that I just gave, you can actually see causal chains as Hawk's processes, which might give us a more mesoscopic kind of way of describing them. Okay, so the consequences that I see, and I'm almost there, the consequences that I see from this kind of thinking is that you cannot define causality for a one-time observation of a simultaneous event. So if I see two events happening at the same time, I cannot say anything whether they are causal related or not. Only if I have more temporal information, I can do that. I think that's an interesting consequence of the definition that I just gave. Secondly, so causality is a function of time, so we should actually always, in my terms, always talk about temporal causality, where the direction of time, of course, is defined by the second law of thermodynamics. And therefore, as a consequence of that, I find that interesting. I have no idea what it really means, but I find it interesting because as a consequence, when we look at it like that, then we will have causal asymmetry, because we know that in classical sense, the amount of information that I need to reconstruct the past is more than the amount of information that I need in order to predict the future. This is a result that was done by people in Singapore from the quantum mechanics group. Because in quantum mechanics, it's actually not like that. The amount of information to retrodict the past is the same as the amount of information needed to predict the future. But as we are talking about the classical system, then causality, then the temporal causality we talk about has this hysteresis, this kind of asymmetry, causal asymmetry, which I think is an interesting thing. Again, I don't know what it means, but it's cool, I think, to be aware of it when we talk about limits, etc. And in practice, I think that there's always a part in the temporal causality which we cannot determine. And the reason is that we need, if we really need to look at the consequence of an intervention that we do in the system, we need to have the exact initial conditions of the system, which we quite often cannot do. And that will, of course, is then directly related to the deterministic chaos that could be in this kind of nonlinear systems if you don't have, accurate estimation of the initial conditions. And that would be in closed systems, and in open systems like complex systems, there is implicit chaos, so it's even possible there. So that's also kind of a limit that you can see there. Which brings me to the last slide, the lessons and the limits from this. So I said I needed 8 minutes. I think I'm almost there. So first lesson, 2 lessons, and then 2 limits. For me, when I think about temporal causality, I think about this thing, let's say functional extensions. We need to make the problem bigger in order to explore. So when you, whatever you're studying, so if we're doing a research about mental health, and then at some point we started to think about, does it matter where you live in the city, or whether you live in the city, or what you have been eating, or whatever. At some point you just want to make things bigger and bigger and bigger. And the question is, can we have quantitative metrics to identify when to stop making things bigger? Because as we know, things are connected to everything, but at some point there might be just a decaying kind of causality there. So processes, and then somehow we have to calculate some kind of associated information metric. We have some ideas about that. We can discuss it later, maybe. But yeah, this is still open research, I think. How, what that information metric should be or could be. If we talk about, okay, we'll talk about it later. Another thing is temporal extensions. So functional extensions should just explain. Temporal extensions, sometimes we just have to wait extremely long for a causal relation to appear. It might just hide for a very, very, very long time and then suddenly pop up. That might be because we just didn't measure the right thing. But it might also be because it's a very sleeping, dormant process. For instance, smoking and lung cancer, of course, is an example. But also, HIV treatment, if you treat people with the hard kind of medication, then the virus basically starts to hide in the white blood cells, and it will be very, very hard to identify that the virus is still there. But then after, a period of something like that, can be like up to 10 years, it starts to manifest itself again. So again, there is this temporal extension. If you want to think about cause and effect, we need to have a better understanding of how to measure, how to quantify that that process of hiding, if you like. Then to limits of data. In my way of thinking, data that we have is dead. It's something that it's a registration of the past. It's something that that was there and it's there, and we can predict patterns from it, of course. Also, we can infer patterns from it. But those patterns will only predict the causal state of a system, future state of the system, if the future is basically the same as the past. But the moment we do interventions, we talk about the change in the system, and then the data that we were looking at is just a completely different data. It's not the data that we have registered before. It's like the Chinese proverb: you cannot step into the same river twice. And the final bullet there is that there is a limit of computing. So even if we know the whole chain of processes, but we have a mistake or an uncertainty in the initial conditions, then predicting the exact outcome of an intervention is still going to be impossible because of these nonlinear expansions that you have. So I guess for me this is just a very brief context of the way I want to think about these things, and particularly these two limits of data and limits of computing, I think, is what Federica asked us to think about. So that's it from my side.
Thank you so much, Peter, also for kind of starting making a link to the second panel on information. So we will certainly come back to this point. Frank, floor is yours.
Thank you, Federica. And I really like Peter's intro into this subject, because I can sort of put a counterpoint to it in the sense that I tend, by my background, to work the other way around, work from measurements and data and try to figure out what it can and cannot tell me. And so explore limitations from that point of view. I would also like to briefly make a slight excursion into physics, in the sense that for me, information about a past event needs to have been able to propagate to the here and now for it to be able to influence me here now. So in classical relativity, you talk about light cones, in the sense that you mean anything that is within a light cone, close enough to have been able to influence me by something propagating with the maximum propagation speed, which is the speed of light, to then influence me. So that goes for the universe as a whole. Now, I tend to think of systems where there is a finite maximum signal speed, which might be different from the speed of light. In many realistic systems, that is the case. If we talk about, for instance, if you do simulations of gases, then the maximum speed at which some information can propagate is the speed of sound. So that it's a different limitation, a different kind of speed. So in complex systems, I can still imagine that there is a finite maximum speed at which one event can inform other, one part of a system can inform other parts of the system into of a change. And I think one of the aims that I would pursue, given my propensity to try working with data, is to see, can data tell me how quickly one part of a system can inform other parts of that same complex system of change? So establish whether there is such a thing as a maximum propagation speed, a typical propagation speed at which events propagate through that system. And of course, as Peter says, if the entire system changes through a big enough intervention, then that speed might well change as well. For instance, it used to be the case that the fastest means to communicate with each other was writing letters. And since the event of the telephone, the speed with which we can communicate with each other has increased. But even so, it still requires you to call up, to dial on the rotary dial. It takes a bit of time. These days, with smartphones and the internet, I can reach somebody in Australia within milliseconds. So that speed has, of course, changed because of the speed of communication between people has changed because of technology changes. But even so, given a particular state of connectivity of a complex system, you could possibly define what the maximum information velocity is, and therefore tell how quick can something have influenced something else. Is there enough time for a signal to have propagated? So that's one thing that that I wanted to mention. And there, I think data is very important to be able to tell you something about how quickly things propagate. So I think that's important to try and establish, even though you might think that it changes over time. Another thing that I thought was important when thinking about the limitations of causality. I mean, if things can't have communicated, there can't be causality. Barring quantum mechanical effects that I'd rather not go into. I think it's also very interesting what Peter was saying, which I, in a slightly different way, also wanted to mention, is that causality has not only a direction, but a size. Some things influence stuff around them more massively than other things, and how to quantify that. And it's very interesting that Peter then moved towards trying to define a work function and quantify causality, and by being able to do work on it, because that for me you would almost want to start looking for whether there are conserved quantities. I mean, in classical systems, you work with energy as a conserved quantity in a closed system. You can work with a second law of thermodynamics where entropy cannot decrease. There are certain conserved quantities and certain constraints on what kind of changes the system can undergo. And again, complex systems, interactions between people do not automatically have that type of conservation, energy of course, but the kind of interaction between people do not necessarily have self-evident conservation laws associated with them. And there I would want to inquire, using data, whether we can infer whether or not there are quantities that we can consider to be conserved in any given complex system such as a society or an economy. And that, I think, is important, because as soon as you can see that a quantity is conserved or can only increase or something like that, it reduces the space of possible states and transitions to other states that are allowed within this system. Rather than being infinite dimensional, you can perhaps push it down to a finite number of directions that a system can evolve into, which again, it might give you exact predictive probabilities, but with something like as classical as the three-body problem in physics, there are it's known that there's chaotic orbits there, so there's limits to how exactly you can predict something, but you can say something about some things that cannot occur, or that are statistically more likely to occur than others. So then you can still constrain the ways in which a system can evolve, the way in which some events can cause others or cannot cause others. So excluding causality is perhaps also in the classical statistical hypothesis verification context. It might be easier to disprove a particular causal relation than actually prove that there was a cause and effect. So those were the prime points that I really want to make. Of course, I'm thinking about that. That's what my background is. I think about big systems in terms of many people or many businesses, large numbers of bits interacting. You could also try to scale this down into all of the interactions within the human body. That's really not my field, so I really shouldn't discuss things like that. So perhaps, although many of the discussions in the previous sessions were about testing whether treatments of people, whether they work, I find those very interesting, but I can't really say anything about that type of system because I simply don't have the experience. So yeah, that's really all I wanted to discuss. Thank you, Federica.
Thank you, Frank. That was again very rich. I suggest we take a couple of minutes for direct questions, and then we move on to the next panel so that everyone can at least listen to all the panelists. If any of you has questions or comments, please raise your virtual hands because it will be much easier for me to see. I think I see a physical hand. Kees, I think Lasse, you also had your hands up. Okay, so Kees and then Lasse.
Thanks to Peter and Frank. It's very interesting to hear what your opinion is about causality or your view on it. And what I noticed is a very big difference in the two views, in the sense that for Peter, it is apparently a condition that you should be able to intervene because there is in the definition of causality a difference between the state with and without intervention. And in Frank's view, I think this is not really necessary, because things are interacting constantly with one another. Light can reach you from anywhere else. And even without this intervention, there can be causality. So I would be interested in hearing your opinions about this.
So if I can react first.
Yeah, go ahead.
Yeah, no, that's I think that's correctly observed. For me, the point is more that so if the past is like the future, so if I discover some dynamics in the data that is still valid in the future, then I can do the things that Frank is talking about. Then I can actually talk about cause and effect across time, so to say. Point is, if I do an intervention in the system, that's not valid anymore, because of that moment I'm talking about a different system altogether. So that's why I try to make that distinction between these two. So I'm not saying that it's simpler without intervention, absolutely not, of course, because it's still very hard to determine those causal relations. But I think it makes sense to at least make a distinction between the two. And that's also because, you know, I was trained as a physicist, so, and like Frank actually. So, so yeah, we tend to think in terms of experiments, right? So you have a system, you ask a question to the system by doing an experiment, you have some idea about what's the outcome, you do the experiment, something else comes out of it, and you've learned something, right? And so, so it's all about cause and effect due to intervention in that sense. But yes, if you don't have data of the future, you have to think about it like this, I guess.
Frank, is there anything you want to add to this point?
Yeah, yes. I think there's a slight difference in backgrounds in that I think Peter is more of an experimental physicist, and as an astrophysicist, you tend to just watch things happen rather than try to intervene. So perhaps you notice that a little bit. I think that Peter's view, I'd like to give it a bit of nuance. I think it's quite pessimistic to say that whenever you intervene, the system is then completely different and you can't use any information of the past to inform you about the current state of the system. There might be cases when this happens. I think that on the whole, not everything is destroyed by interventions, and you can use the past to inform you about the future. And ideally, you would want to say, I give a certain amount of weight to the knowledge that I built up out of the past, but I don't let it fully determine what I think the future will be. I acknowledge that there will always be things that I was fundamentally incapable of measuring, or that interventions effects that I'm uncertain about. So while not abandoning everything that I've known and learned until now, I'm not going to give it 100% of the weight. I'm not going to pretend that the past will lay down the future with complete certainty, and then finding that balance between using the past, knowledge built up out of the past, to a limited extent. That balance is where the real black art is of how well you can predict systems, or how well you think you can predict systems.
Yeah, but if I briefly can react to that, I think the crux is in your remark that yes, there is a limit. Yes, there is a limit to what we can do with the data of the past to predict the future, and not for every system. But that's the crux. And I think if we look back the video of the presentation by Joris Moy, I asked basically the same question, and Joris said, you know, it is true, we cannot completely predict the future out of the data of the past, but what I am doing, he said, is look at what are the limits of what I can get out of that data. And I think what I'm saying is that there is a limit to those limits.
Okay, thank you. Lasse, do you think we can postpone your question to the general discussion, or is it a quick one that we can try and handle now?
What if I say no? Try. No, it's all
Okay.
right. It was actually my question was very much in line with the case just asked, so we can just move on, and if there's time, then I would like to get back to that topic.
There will be time. I'm trying to make the time. Okay, thank you so much.
Okay.
Let me unpin our first two panelists, and then where is the pin now? I can't unpin Frank. Why? Can you unpin yourself? I don't see the button anymore on my screen. Oh my god. This is very strange.
Not even sure.
Remove
You
me.
can-
I
Okay.
know where
No,
to
it's
find
fine. It's fine. It's done. It's done. Okay, so John and Rick. Okay, so maybe in alphabetic order. John, do you want to start?
Sorry, sure, I'll do. I'll share my screen.
I may have to give you powers. Oh, no, you can. Fantastic.
You already did, I guess. Thank you for that.
Yeah.
Okay, so here is my presentation. I thought when the previous session is about systems, and when you, Federica, raised the issue of information as influencing, why don't I focus on that topic? That means I won't say anything much on my contemporary research per se. But I could have talked then, by the way, about temporality, but that I didn't know beforehand. But I will present some classic insights that underline lots of my work over the past 20 years or so. And hopefully that helps also to bridge between the different disciplines here around the table. Okay, so here is the first basic issue about information as influence. Again, that's your own input, Federica, here at the end of your presentation. And there's a classical view, of course, that was closely related to cybernetics, fueled by Bateson, who said this means that information is being seen as a difference that makes a difference. Well, the classical example is a cybernetic system like an automatic pilot. There is a norm, which is mentioned here in input, but actually it's a norm. The system does something on reality. That is compared with the norm, and if it deviates, it corrects. Yeah, that is, of course, the classical example of information being a difference that makes a difference. The point is that in any social system, it doesn't work that way. And here I'm following very quickly the argument made by Sir Geoffrey Vickers, who was an engineer trained in cybernetics, leading the reform of the British coal sector after the Second World War, for instance, on that basis. And then after his retirement, becoming a professor at Yale and reflecting on all that. And then one of the main outputs was this particular book called The Art of Judgment. And there he basically said, in social system, there is a decision that makes a difference. There's nothing like any automatic response to, for instance, the difference between reality and the norm. There's always a decision in between that. You can act on the difference or ignore it. And if you act to what objective, towards what objective do you act? A decision then is always informed by judgment. And in that judgment, information is being interpreted. It's got meaning. And that judgment is the next step in this argument, is shaped by an appreciative systems, which is the readiness to distinguish some aspects of the situation rather than others, and to classify and value these in this way or that, as he puts it. So basically you ask, what do I see and how do I like it? Yeah, and so that means you give meaning. Finally, appreciative systems are shaped by a web of concepts, artifacts, and so on, in which this process takes place. And here is your energy field, Frank, that brings the past to the present, and helps us shape the future on basis partly of that past. That, by the way, is of course what happens, Peter, if this force operates for some time and changes the energy field of the system. I would say there is the parallel between your two arguments. Yeah. Okay, so that comes in here in social science. In this particular way, it shapes the interpretations and therefore mediates between the state of affairs per se and how it is being acted upon. Yeah. Well, then Frank Fisher is the next one to treat, but the bridge to him is this small picture about the Q fever a few years ago. Here, like in earlier animal pandemics, at some stage somebody on television said, this means we should not further expand organic livestock farming. That was weird, because this did not occur in organic farms. It occurred in intensive husbandry systems. So why did they say so? They said so because the assumption is that a pathogen traveling around through the country will have an easier job in organic farms than in intensive farms. And it has, so that's the assumption, because these animals are not vaccinated, for instance. They are going out in the free in the open, so they may get the pathogens, they breathe it and so on. That's the argument. Obviously, an organic veterinarian doctor, so a doctor would say, well, let us be, what we are doing is increase the immune system of these animals, so we can deal with that. And it is being increased by intensive agriculture because of the densities of cattle. Yeah, that means that indeed here we have an example of how judgment is being shaped by the social context in which you find themselves. Most veterinarians have been trained at the university that was preparing their students for the intensive husbandry system, because that is 98.95% of the system, and not for the other systems. So they have, they are basically drawing their arguments and interpretations from that field in which they find themselves. Yeah. Well, now Frank Fischer, how can we evaluate particular claims? Well, he was looking for a framework that comprised causal relations, meanings, normative beliefs, and deep preferences. So here's what he's doing. He's basically saying there's 4 layers of argument that we normally make, partly implicitly. The most explicit normally is the first 2 layers are situation specific, for a particular problem area, a particular issue. We have there first and foremost what he calls technical verification. This is empirical analytical argumentation relating causes to their effects. Yeah, and that is indeed empirical analytical sorts of arguments. There's also situational validation. That is about meaning. What is the meaning of this particular situation? That requires phenomenological argumentation in epistemological terms. Yeah. So what beliefs do we bring to the situation here? And you can discuss this, and then you're scrutinizing the situation, and you can refer to the facts of the situation, so to say. So there is an empirical support argument possible, but it is not only about empirical analytical argumentation. Yeah. The second 2 layers are more generic. We bring them to bear on many different situations, not only on this one. 2 layers again. The first is what he calls societal vindication. Then the question is, what are these beliefs precisely? That was part of the phenomenological argument. We here assess these beliefs. What sort of social order do they produce? If we act on these beliefs, what sort of society are we going to live in? Yeah. And then finally discussing the merits and the limits and so on of that society is the social choice layer. And any claim actually is implicitly about all these 4 layers. And what you can do for a claim that, for instance, is only explicit on the previous 2 layers is ask these questions, and then you will have a critical discussion on that particular claim, underlying its core assumptions, and also addressing what sort of society they correspond to. You, for instance, could discover here that we are now talking about animal health and illness in a way that reproduces intensive agriculture. And then we may or may not like that, but at least we have, and that question is the social choice question. Yeah, so that's how he builds up the argument. That, of course, reminds us of Jürgen Habermas, who said that rationality means that we can do such a critical analysis, bringing together causal claims, meanings, underlying beliefs, and so on. And that is interesting because that also means that this does not necessarily take us to relativism, because relativism would be there if anything would go. But we're not doing that. We can have a very precise discussion about what sort of context do these beliefs correspond to, what sort of context do they reproduce, and there's, again, in addition to normative considerations, a lot of empirical analysis in that. So not anything goes, but there are definitely ways to have a much better discussion than that, and that precisely analyze his communicative rationality or deliberation. And that then would be one way to move forward when there are different claims on causality. Yeah, that's also how to understand how I first, Peter, understood your example about AFE. It appeared to be in the blood, white blood cells, but I thought it was about the responses of people to the, well, there's a drug anyway, so it can be less careful. And that would be fitting this particular story. And then, of course, discussing that rationality vis-a-vis that of the medical sector, who probably would not advise to do so because of the blood cells, would be precisely deliberation. And it would be an interesting question to see where that would take us to, also in terms of a more wider understanding of HIV, for instance. Bringing together these different ways of looking into it. Well, finally, taking us back again to information is influencing. One implication for all this is that we do not just absorb information and act on it. Yeah, that's precisely what Sir Geoffrey Vickers put his finger on, and what I've elaborated in between. And one grand old lady from the policy sciences who has become famous with that some 40 years ago was Carol Weiss, who died a few years ago. And she had been doing, she was at Harvard School, or at Kennedy School of Government, and she had been doing a lot of evaluation and noted that in many cases her recommendations were simply not followed up, and she started to wonder why. So she did a major project interviewing hundreds and hundreds of people using her and other evaluations and trying to flesh out what happens. Yeah, and she found, quickly summarized two things from the title of an article, and there I'll end, Federica. Knowledge creep and decision accretion. Knowledge creeps because it enters our mind, but by finding its way in between what we already knew. So sometimes it corrects something we already knew, sometimes it adds to it, but it has to somehow relate to it. It has to become part of that force field in our own minds. Otherwise, we won't absorb it, and we won't certainly act on that. And that's what she very clearly found. We will not just act on things instrumentally if somebody tells us, because if that doesn't fit our thinking, it doesn't mean anything sensible to us. Yeah, so we simply won't do that. Yeah, that's what she found empirically. And the other thing was there is decision accretion, and that again takes us back to this force field around us. Yeah? Even if a piece of information does something to us conceptually by helping us to think a bit differently on an issue, then that does not necessarily mean that we take another decision, because this force field, this energy field around us matters. And that's called decision accretion. Decisions grow very gradually in a particular network. Well, that was my 2 cents.
Okay, thank you, John. Rick, do you want to share your screen, or is not needed?
It's not needed. I thought I was not even allowed, so I did.
Well, you can see how they are behaving, our panelists today, but it's fine. We are a happy family after all. Floor is yours.
Yeah. Maybe I should have been more rebel myself as well. So information. Well, thanks, John, also for paving the way a bit for me, and also Peter. And so first, so information, right? This is both a very easy question, but also a very complicated question to answer. What is information? And what John just presented reminded me of perhaps even the existence of, so I'm freewheeling now, perhaps a kind of an existence of a kind of quantum versus classical definition, which may at first not seem congruent, but maybe perhaps in the end they are. So what do I mean by that? So first, if you ask me what is information, I can imagine that there's two definitions which were reflected in John's presentation. One is the very, let's say, high level concept. It is what people colloquially refer to as information. Like I read a web page about some topic like organic farming, and then I take information to me. Yeah. People don't necessarily have a very exact definition of what this means, this information, but it is kind of intuitive what they mean. And then they say, okay, I take this information, and then my processor will kind of look at it and make a decision. A second definition, which I would consider a bit more low level, is the fact that there is a mathematical definition of information, what it means by Claude Shannon and also some others. Quantum, you can talk about maybe Renyi entropy, but at least there are, let's say, a handful of mathematical definitions which are exact. And now the question is, of course, are these two congruent? Like, can I speak about the mathematical definition and explain how people reason about information at the more high level, and perhaps even vice versa? So that is a question that I don't have an answer to, but I thought maybe I spent a few minutes to at least maybe explain a bit more on the low level side. So that was more towards the early phase of John's presentation, where he was speaking about the difference that made a difference. So what is this low level information? So this low level information I see as relating to possibilities. Yeah, so it's actually quite very simple, the definition. So information is about possibilities and the reduction of a number of possibilities of some system, right? Doesn't care about what. So for instance, if I would flip a coin in the air, before it lands, there are basically two possibilities about the outcome. But as soon as it lands, there is only one. And this difference between these two situations we call information, right? We have reduced the number of possibilities of a system. Now that is information. Now the question is, how does that relate to causality? And I think there are two important considerations about this. One, imagine a causal link. So for instance, Federica has a strong magnet under the table and a wire to it with a button. And then she acts as a kind of Maxwell demon, where as soon as heads start to rotate upward while the coin is still in the air, Federica will very quickly push the button and make sure that with the magnet that the coin ends up heads. Now, what happened here is that for us, all who is not Federica, there were still two possibilities. And then after that, there was one possibility, namely heads. But Federica already knew that it was going to be heads. And this information was in the brain of Federica, somewhere stored, I'm not sure where. And then suddenly it travels through the system, through the button, through the copper wire, through the magnet, into the coin. And now this information is, so determining the state, reducing the possibilities, now is in the coin, whereas before it was in Federica's brain. So there is this flow of information, which we would say is causal. So if Federica would have different information in her brain, then there would also be a different outcome in the coin. So that is one way, one, I think, profound way in which information relates to causality at this low level again. The second, I think, is the fact that this is a type of, it seems to be a very universal concept, right? So because we're studying all these kinds of different complex systems here, and what often happens in causal inference is that there are assumptions made. So for instance, how does a system work? And then using those assumptions, I will make a causal inference technique. For instance, I know that the causal relations are roughly linear with Gaussian noise. Therefore, I will make a regression analysis and then infer causal links, or I will make some kind of conditional independence study, statistical, in order to infer causal links. All kinds of assumptions enter into causal inference, and without assumptions, we cannot do causal inference, is one of the assumptions that people make. But this information concept, that is something that easily transfers from one domain to the other. So in that sense, I think it has the power to, if we learn lessons in one domain, maybe we can easily transfer it to other domains, because this information concept is model free or domain free. So I think that is an important second ingredient to why I think information is very important. It's also already entering into the causal inference field, but not yet very prominent, but I think it is definitely growing. So that I think is important. Yeah, I think that is that. And then of course, the question is, okay, how to infer these information flows from data. And there we enter, I guess, into similar discussions like what Peter and Frank were talking about, that for instance, you would have to compute this from data that you have already, and then transfer it into what you think will be the new situation. And one note that I could link to that is that so often what happens is if you make assumptions, again, you make strong assumptions about the system, for instance, linear plus Gaussian noise, let's make it simple. In that case, if you make these assumptions and you're happy with it, sometimes extrapolation is pretty easy, because extrapolating a line with Gaussian noise is not very difficult. And if you made this assumption in the first place anyway, you're happy to do this. But if you don't want to make assumptions about the system, and information is one way to be almost, let's say, assumption free. So it's in terms of number of assumptions that I'm willing to make about the system, it's about as low as one can get. If I do that, then suddenly this extrapolation question becomes much more relevant. And I should not anymore be comfortable stepping outside too far of the scenario where the data was collected in order to make inferences. Because I don't have these strong assumptions that tell me, yes, that's perfectly okay to do. So I think using this concept of information theory is very powerful, but it also implies that in the picture of Peter, we stay close to the scenario where the data was collected. We cannot travel too far. If we would travel too far, we would have to kind of maybe make a series of interventions where we make small interventions, then again, collect data, again, make small interventions, etc. So a kind of series of slow interventions that bring us from one end to the other instead of one big one and then see what happens. So I think, so I hope that somehow was helpful these few minutes.
Thank you so much, Rick. That was very useful and very clear. So let's take a few minutes to direct questions to John and Rick, and then we open the general discussion. Does anyone want to kick off the conversation here? Sonia, please.
Yeah, I have two questions actually. So one is maybe start with the last with Rick's story, so that the notion of information that we know, I mean, so there's the syntactic, we call it the syntactic and semantic notions. So the syntactic one is Shannon, and we measure zeros and ones, strings of bits. And the semantic one is the one where we give meaning. And so the story that you tell us about the low level, where we reduce possibilities and information increases, I would actually put that at the semantic account. That's exactly in line with the one that we use in our logic setting. Epistemic logic, for instance, the notion of knowledge is exactly defined. Knowledge increases when the possible worlds, all the possibilities decreases. So, but we wouldn't call that the syntactic notion. I mean, we don't do that in terms of information Shannon style of information. So that's maybe the first thing to ask you, how do you link them? Because there is a huge debate in philosophy to link the syntactic and the semantic accounts. So, so that's an interesting point. Yeah, no, and then indeed, of course, so that causal inference. So we are studying causal inference in the logical systems, and specifically also in these epistemic logical systems that are based on that notion of knowledge or linked to that type of notion of semantic information. But it is interesting to see that the same notion would appear in other areas as well. So, and I agree that this is cross-domain. So that's the first thing about the syntactic and the semantic differences.
Yeah. Okay. So yeah, actually, I was going to ask the first question to you. So now we have a situation where we both cannot answer this question. But I think that, let me try to think about it. So the knowledge type of scenario seems to suggest that there's one realization, right? So there's one realization of the world. I gain some knowledge, and to me then.
Well, so we use the coin example in our classes. The coin example is exactly what we use. So there are two possible worlds. The coin lands heads, and the other one, the coin lands tails, and it's a fair coin, so it will all other heads of tails. So my uncertainty covers these two possibilities. that when the coin is uncovered or I observe what the outcome is going to be, it reduces the possibilities. And in this case, it reduces heads and I keep tails, but it could also still leave some options open, right? And it can be different for different people who have not observed the same thing. So it can get pretty messy. So the model can get very complicated depending on how many agents you have and who knows what and who learns what. So it's reducing this uncertainty by observing something or by gaining new information. So you gain information and then you decrease the uncertainty. Yeah.
Sorry, I thought we were finished. So yeah, to me it sounds a bit like relativity or so, right? Like it depends on the observer who has knowledge and therefore the amount of possibilities that you perceive, right? Because for instance, in my example, I just realized that I also mixed the two kind of silently, where I said that to us, everyone except Federica, it seems that there is information being produced, whereas in fact in the ensemble setting, the entropy of the coin should be 0 because it will always land heads, and therefore, yeah, even though we don't know, but in principle the system doesn't have entropy there. But to us it does seem like so. Not knowing what Federica is doing, to us it seems like it was an uncertain outcome and then it became certain. So this kind of observer dependence, the definition of information would have to be defined, I suppose, because without this, normally there's no observer dependence of the difference.
Yeah, no, well, okay, of course, in philosophy also and epistemic logic, things are more complicated because there might be a state of the world which is there and we don't know about it and it comes about, right? And to have true knowledge, it should be true. Else I can have a false belief, etc. So the notion of knowledge that you get in the end and the mechanism that guarantees that we actually talk about knowledge means that it's true dependent. So it would relate to the real state of the world, even though I might not be aware of which of these possibilities is the real one. So, but that's we model that externally. I mean, of course, it's independent from the agents, from Federica who does the experiment or the others that are watching it. So it's the modeler who puts a coin. It's like you say, okay, entropy is 0. I put a little star and say, this is the real world.
Yeah. Yeah.
But this is where I see Esther saying, yes, exactly, you have to specify who is saying this because the role of the observer or of the researcher is crucial. So somehow we go back to a debate we had last time. And it is really a subtle point about the extent to which you can really separate the perspective and what the world really is like, if we can ever get to that point. But it is interesting that this comes back via a different route, namely whether we can draw a distinction between this semantic and syntactic understanding of information. So nice that this problem comes back differently. Okay, maybe let me unpin the panelists so that we can move on to the general discussion.